Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about Green's functions in the time domain and see how we can derive those from the Green's functions in the frequency domain. And what we will need to do is just make a Fourier transform of the Green's functions in the frequency domain, which we used in the previous lectures. So we have seen that we can relate the Green's functions in the frequency domain to the band structure and densities of states, and with that can derive material properties from an estimate. And we have been talking mostly about particles that we create and propagate, although we wrote down our functions in the frequency domain. And let's now make a Fourier transform to the time domain to really show that what Green's functions defines are the propagators of your system, how particles propagate through your system, or in the frequency domain, the Fourier modes of the propagation of your system. So we want to calculate the Green's function in the time domain, and let's start by looking at the Green's operator and then calculate expectation values of those operators to get the Green's functions. And we'll define this as the Fourier transform of the Green's function in the frequency domain, e to the I omega t g plus of omega d omega. And our Green's operator is defined as 1 over omega minus the Hamiltonian plus the ground state energy plus a small imaginary offset, such that we know where the poles of our Green's function are. In order to calculate this integral, we will use the residue theorem. And what the residue theorem tells us, if we have an integral over a contour, a closed contour, going anti-clockwise of a complex function in the complex plane, then we can have a look at the poles of our function, and all poles included in the contour. We can have a look at the residue, and we sum over all poles the residue of that function at the complex value where this function diverges. And fz needs to have isolated poles of the form alpha k, our residue, divided by z minus zk, where zk then is the complex number where your function diverges, and the residue at that point is alpha k. Now in our case, we have in the complex plane our Green's operator, which has poles wherever the Hamiltonian has its eigenstates, and as our Hamiltonian is Hermitian, the eigenstates are all real, so we have poles slightly below the real axis. So this is where our poles are. And we have on the horizontal the real part of our frequency, and on the vertical the imaginary part of the frequency. And we are interested in the integral over the real axis. So that is the integral that we want to calculate. Now, in order to use the residue theorem, we have to make a closed contour, and we can make two different closed contours. We can either look at 1 over 2 pi, where we integrate over the upper half. So we have to close the contour in the upper half plane of e to the minus I omega t, there is a minus missing here, sorry for that, of g plus of omega d omega. There are no poles within this contour, so I know that this integral will be 0. I can of course also close my contour in the lower half plane, where we integrate clockwise, so you get an additional minus sign here, and that's 1 over 2 pi, the integral in the lower half plane of e to the minus I omega t g plus of omega d omega. And this is minus 2 pi I times the residue of 1 over 2 pi e to the minus I omega t g plus omega. So let's have a look at the upper half. If we can show that the integral over the arc is 0, then we can relate the integral over our contour to the integral that we are after. So what we know is that the integral over our contour of e to the minus I omega t g plus omega d omega is 0. Therefore, the integral that we want to calculate, e to the I omega t g plus omega d omega, is equal to minus the integral over the arc, e to the minus I omega t g plus omega d omega. In order to calculate the integral over this arc, we're going to replace omega by polar coordinates, where we take r0 times cosine theta plus I sine theta, and we have r2 let r0 go to infinite. The integral over the arc, e to the minus I omega t g plus of omega d omega, is then given as the integral of 0 to pi e to the minus I r0 cosine theta plus I sine theta t g plus omega r0 d theta. Which is equal 0 to pi, we can multiply these out, e to the r0 sine theta t e to the minus I r0 cos theta r0 g plus of omega d theta. We'll take the limit of r0 to plus infinite, which means that this becomes a large value multiplied with some phases when t is positive. When t is negative, we have e to the minus infinite t, or e to the minus infinite, that will become 0. So for t equal to 0, this will suppress our integral, and that integral will be 0. So this is for t smaller than 0, 0, and that is exactly equal to the integral that we were after. So we know that g plus for t smaller than 0 is equal to 0. So from the upper half we can derive that our Green's function in the time domain, or the Green's operator in the time domain for t smaller than 0, is 0. Well, for t larger than 0, we have some value here for the arc, which is not an easy integral to evaluate, and therefore you'll have some value for the integral that we were after, but there's not much that we can learn from this contour for t larger than 0. For t larger than 0, however, we can have a look at the contour integral where we close our system in the lower half. Because we know that if we look at the lower half, then for t larger than 0, the integral over the arc is going to be 0 for the same argumentation that for t smaller than 0, the integral over the upper arc will be 0. Here we look at positive complex number, for positive values for the imaginary part. Here we have negative values for the imaginary part. So for the contour integral in the lower half, we have an additional minus sign here. So t has now to be smaller than 0 instead of larger than 0. T has to be larger than 0 instead of smaller than 0. For that integral to go to 0. So we know that g plus for t larger than 0 is 1 over 2 pi times the contour integral in the lower half of e to the minus I omega t 1 over omega minus h plus E0 plus I0 plus the omega. We just took the definition of the Fourier transform of our Green's function from minus infinite to plus infinite, and we've added the contour integral over the arc because that is 0 anyhow, and now we have a closed contour interval. So now we can use the residue theorem. This is minus 1 over 2 pi times 2 pi I. The minus comes because we're closing the contour clockwise and not counterclockwise. And then the residues at e to the minus I omega t, 1 over omega minus the Hamiltonian plus E0 plus I0 plus. Well, we have a pole when omega is equal to h minus E0. So we find there an omega minus, for omega equal to h minus E0. So what we have here is minus I e to the minus I h minus E0 t. Putting this together for t larger and t smaller than 0, and we find that our Green's operator is equal to 0 for the case that t is smaller than 0, and minus I e minus I h minus E0 t for positive times. And we can also write this with the Heaviside theta function, which is 0 for t negative and 1 for t positive, e to the minus I h minus E0 t. So that's the Green's operator. Now have a look at our Green's functions. For that we need to take the expectation value, g plus tau prime t is equal minus I theta t, and then we take the expectation value where we have our ground state wave function. We create a particle in the quantum state tau prime, we annihilate it from quantum state tau, and we have e to the minus I h minus E0 t in between. This is e to the minus I times minus e, so that's e to the I E0 t, which is just a number, so that we can take on the other side of the operator. So that we have e to the I E0 t, annihilating the particle e to the minus I h t, creating the particle psi 0, e to the I E0t, that is the Hamiltonian acting to the left. So this is psi 0 e to the I ht, because when h acts on psi 0 it becomes the energy of that state. At e to the minus I ht a dagger t prime psi 0. And what we have here is nothing else as an operator that is time dependent in the Heisenberg picture, psi 0, removing the particle at time t after creating the particle at t is equal to 0. E to the I h t is equal to 0 is just 1, so that we can always replace the particle in the Schrödinger picture by the particle in the Heisenberg picture at time equals 0. So our Green's function, G+, tells you if you create a particle in quantum state tau prime at t is equal to 0 and annihilate it at time t from quantum state tau. So the expectation value of creating a particle somewhere, having it propagate and annihilating it at some other place. If you try to annihilate it before you create it, it always becomes 0. That's what your theta function does. And yes, there are some phases in there that we need in order to make all the Fourier transforms work, so that we get all the phases right and can relate our Green's functions in omega space to the densities of states and the band structure. We can look at the propagation of an extra electron with G+. We can do a similar derivation for G-, and if we just go through the math, but now with G-, then we find that this is I theta t minus t psi 0 a dagger tau prime t is 0 a tau t psi 0. So we annihilate the particle at time t, we let it propagate, then we create a particle at time t equals 0, going from quantum state, that's tau to tau prime, and when t is negative, then you can create it at time t and annihilate it, or you can annihilate it at time t and create it at t equals 0. When t is positive, that becomes 0. So again here we see that G- looks at the propagation of holes, where G+ looks at the propagation of particles. So indeed, this idea that your Green's functions tells you how particles propagate through your system completely works. We'll do most of the mathematics in frequency domain, because there, because you look at eigenstates, states don't interact with each other anymore. The math is often simpler. Nonetheless, when I talk about Green's functions, I often say, well, you create a particle here, you let it propagate, and then you annihilate it, because I know that you can always Fourier transform, and that is for me the more intuitive picture of what's happening and what you're looking at. But in principle, you just look at the Fourier modes that describe the propagation of your system. So the eigenstates that we look at, and the eigenstate energy. So far for our Green's functions in the time domain. In the next lectures we'll see how we can start to use this building of Green's functions to do some actual physics and solve some problems. Thank you very much, stay healthy, we see each other in the next lecture.